So I'm going to do this problem, and it seems like pretty straightforward. How are we going to do it? Let me get a pen. The water pump generates a constant flow Q, which is currently causing a turbulent spray 3,200 out of the cylindrical nozzle. Which of the following three nozzles could be substituted to achieve a streamlined flow? So we've got three different diameters. Okay, it's not radius. Oh, Reynolds number uses diameters. It's okay. So all we're going to have to do is plug it into the formula and do a comparison. See what gets us less than 2,000. We move on. So let me pull out the equation. I'm going to draw a line here. I'm going to do this problem twice. Okay. And I'm going to tell you already that I'm going to do it wrong first. So you're watching this and wondering what is wrong about what we're going to do. So we're going to say the Reynolds number is equal to 3,200. That's given. And the formula for Reynolds number is rho d V average over eta. And they told us that you've got a tube that has a diameter d. There's a constant, there's an average velocity, eta, 3,200. The next one, the next tube, has, what's the Reynolds number of the next tube? Well, the diameter is, what's the diameter supposed to be? 2d. So, okay, we're going to have rho times 2d, average velocity, eta, and then we pull out the 2, and we realize that that's just equal to rho d V average over eta. And that would just, what's in parentheses is the same thing that we have in the first line. So that would be 2 times 3,200, which is equal to 6,400. That Reynolds number is larger than 2,000, so it would be turbulent. Okay? Then we do the second one. And we say rho, the diameter is now 1/2. Average velocity, eta, this is equal to 1/2 of the stuff in parentheses, which would be equal to 1,600. Hey, this is less than 2,000. Okay, good. And the third one would be equal to rho times 1.7d, that's what's given. The average velocity over eta would be equal to 1.7 times the stuff in parentheses, which is the same as the first line, which would be 1.7 times 3,200. You pull out your calculator, and you get 3,200 times 1.7 equals, some very big number, 5,440, which is greater than 2,000. So you would have said only the second one. But I said this was wrong. Where was the mistake? The mistake is, let's look at the problem more carefully. A water pump generates a constant flow Q. And you're varying the diameter of the tube. That's going to change the velocity, right? If you've got a constant flow in all of these 4 tubes, which one of them would have the highest velocity? Q is equal to velocity times area. Velocity is going to be equal to Q divided by area, which is equal to Q divided by pi r squared, which is going to be equal to 4Q over pi, the diameter squared. So the one with the narrowest diameter is going to have the highest velocity. So number 2, which we figured out was, we thought had the lowest Reynolds number, may actually not, okay? Why? Who's following? The point is that there's not a constant velocity, there's a constant flow. In this wrong way, what I assumed was this V average was the same in all cases. So now we're going to have to redo this. Okay, correct. We're going to say Reynolds number is equal to 3200 was equal to rho d V average over eta. We've got to get rid of that average. We've got to replace it with Q over area, which is going to be equal to rho d Q over eta A, which is going to be equal to rho d Q over eta pi d over 2 squared. We write that and we get 4 rho Q over pi eta d squared. D squared? No, d. The d's cancel, right? The d on the top, the d squared just becomes a 1 over d. So the relationship changes. 4 rho q over pi eta stays the same. We're just changing the diameter. So in the Reynolds number of the number I, we are going to say 2d. We're going to get 4 rho q over pi eta 2d. We're going to rewrite that as 1/2 4 rho q over pi eta d, which is equal to 1/2 of 3,200, which is equal to 1,600, which is less than 2,000. Let's try the next one. Reynolds number of the second example. 4 rho q over pi eta d over 2. We rewrite that. 2 times this. I'll write it down. 4 rho q over pi eta d, which is equal to 2 times 3,200, which is equal to 6,400. It's greater than 2,000. So it's going to be turbulent. The Reynolds number of the third case, okay, is going to be 4 rho q over pi eta 1.7d, which is equal to 1 over 1.7 times the stuff in parentheses. And this time I'll just write it as 3,200. What do we get? Let's see. 3,200 divided by 1.7. 1,882. It's less than 2,000. So the first and the second example have a Reynolds number of less than 2,000. So they are going to have streamline flow. So the answer is E. Whoop. E is the answer. Can I make it as bold, more bold than that? Interesting, huh? This is an example of how you know, if you had done it the first way, you would have thought you did it right and that the answer key was wrong or something like that. You would have been pretty surprised. But there's a trick to it, is that as you reduce the diameter of a nozzle, the flow rate is going to increase. And so not only the diameter changes, but the flow, the velocity did as well. So we had to rewrite that formula. Tricky.